Hey guys, in today's replay we're going to be checking out lesson 20, prochirality, which is, as you guys all recall, prochirality is one step removed from being a stereocenter, but we're going to see a little bit of a modified version of what that is in today's lesson, and we're going to be analyzing a student from the 5 p.m. discussion. So if we go ahead and just kind of see what's going on here. So we can see that there's a Marvin view with a couple of different boxes with this, and the student does a good thing and he immediately sees how much time he has, so that's, he's going to gauge how much this question is going to require and kind of time himself accordingly. In the first question, well, the good thing here is he opens this box up and gives himself a really big view of what's going on. Everything is starting from the very left box, and we can see that we have a linear precursor here. In the first drop down, we're asked about an intramolecular elementary step, and this is facilitated via a chiral promoter, CP, and we're going to notice a couple of things here. So the first question, or the first fill in the blank, the student is just checking out his options, and immediately we can so you go straight to the SN2, and when you see a primary halide in that situation, we're going to know that we're going to be breaking that off. So SN2 there is good, and the one thing the student here now is looking, and I guess for him he was looking at the formation of S1. So the chiral promoter is somehow biasing this precursor to cyclize into the S1 fashion, and that's just going to create an enantiomer to anything that R1 is going to propagate. So here the option is array and psi phase, and this is, so I'm going to pause here for a second, and this question, ultimately we're dealing with prochirality, and as you can notice, S1 and R1 both are technically not, they don't contain any stereo centers. So the first thing is, we're thinking, okay, how is this related to prochirality? And the way the authors presented it was kind of from a molecular orbital standpoint. So we can see that that is going to undergo an intramolecular SN2 attack, and what the important thing to notice is, where is that sigma star? So the lone pair on the nitrogen is going to attack the backside of that CBr bond, and it's going to be essentially an N2 sigma star sigma type interaction. And the thing is, it's that ultimately is going to set up the way that the linear precursor is going to cyclize. So if we kind of go ahead and see what the student was thinking here. So the student has about 4 minutes remaining, just thinking, okay, how did I get to S1? And if you take a closer analysis, you're going to see that there are two ways to cyclize. Looking at it from the way we are, and looking at it from the backside of that vinylic carbon that's connected to R1. So here the student has that it approached the psi phase. So ultimately what that's saying is the sigma star is positioned in a way that it's approaching from a certain phase of that that essentially prochiral center R1, the carbon that R1 is connected to. It's approaching either in the array or the psi phase, and the student has chosen the psi phase, but that ultimately is going to give you the R1 configuration, and hopefully he goes back to the first box. But if he doesn't, go ahead and label your priorities about the vinylic carbon that is connected to R1. The next option was a certain type of rearrangement, and as you can see, going from S1 to enantiomer 4, which is what the question asks, you can see here this pi situation, this pi bond here, in the fashion that we would expect a 3-3 to happen. And what we can do is we can kind of look and see how did that undergo a 3-3 sigmatropic rearrangement. And here we notice that these double bonds are going to interact in such a way that's going to give you an enantiomer 4 from the 3-3 sigmatropic. Just for clarification, the nitrogen approaches the ray phase to form S1. So go back and think about how we can get from the linear precursor to S1, and think about it from the perspective of where is that sigma star situated, spatially speaking, and in which phase is that nitrogen going to approach as it's cyclizing, how is it going to approach that sigma star? So initially the student said that it was the psi phase. We're going to see that that's not correct. So I encourage you guys to go back and ask yourself, how is it really the ray phase that is that is the nitrogen is approaching there to cyclize to form S1. Next, we are asked for in the second step, the creation of enantiomer 4 from S1. We have the ray or the psi phase of the carbon with a double bond containing R2 forms a bond with the ray or the psi phase of the carbon with double bond containing R1. So we can see that you have to ask yourself, where exactly is the point of connection? So here we notice that this nitrogen containing ring forms a 5-membered ring here, and we can kind of look at S1 and say, okay, here's the nitrogen, here are the methylene carbons, and then so the points of connection are going to be at this carbon, this phenylic carbon that is connected to R1, and this carbon here, which it's in the same double bond that is connected to R2. So we're asked to find the ray and psi phase of the interior faces of this cyclized S1 molecule there. So we'll kind of go ahead and see what the student is doing here, and I'm going to bring up a point about some generalizations that I think a lot of students make concerning ray and psi, and also the subsequent R and S configuration. So student goes to the mechanism calculator. Not a bad idea. Let's see what the student is doing. Okay, so looks like he's drawing a 5-membered ring there, kind of to capture this molecule here. And what he's doing is he's going to kind of recreate enantiomer 4 and see what stereocenters come about from there. And we're going to see why you can't distinguish ray and psi phase from the subsequent stereoisomer, or the stereocenters that get created. So in this situation, he has somehow deduced that the S configurations are at this stereocenter here, and I'm not exactly 100% sure if that is the correct stereocenter. It would have been nice if he turned on the RS labeling in the Marvin view, but either way, we can't distinguish ray and psi phase from R and S descriptions. Those are completely independent, and I think a lot of students make that generalization. So here, since his initial thought process was, okay, we have the S stereo configuration, and so we're going to be attacking from the psi phases. As we know, that is not the correct thought process, but the student is going with it, and I think he's going to look at his time for one last moment, but as he's running out of time, I think he is somehow concluding that this is going to be his answer. He's checking it one last time, he's prioritizing, and hopefully he can see, okay, so now he's thinking about changing that last box there. checks his time, he doesn't have any time. So a couple things to think about here. Always be cognizant of how much time you have. At first he did a good job with thinking about his time situation, and that's always good to know, to gauge that. But go back and really describe and provide the correct priorities about the carbons that are being asked for the various ray and psi descriptions. So once again, in summary, ray and psi faces are independent of the stereocenter that get created. So you can attack the ray face and get the R or the S configuration depending on the substituents, depending on what the incoming nucleophile is, and so on. So hopefully that gives you a better understanding of ray and psi. And this question was a little bit of a modified prochiral question, but the authors do describe it. The initial ray and psi attack, as far as the linear precursor cyclization, based on, in my best educated guess, that where is that sigma star located, spatially speaking, and how is that the nitrogen going to make a connection with that sigma star, and that's the face depending on where that sigma star is, and that's the face that's going to be approached. And then we have these cyclized intermediates, and then from there you have very, very awesome chemistry going on as far as 3,3 rearrangements. There was a couple different examples that the authors had provided based on the cyclized intermediates. So anyway, thanks a lot, and hopefully that gives you a better insight into ray and psi and prochirality.